Before we get started understanding Gauss's law, let's remind ourselves of the actual quantities we're dealing with. So D is the electric flux density in coulombs per meter squared. Rho V is the volumetric charge density in coulombs per meter cubed, so the amount of charge in a little infinitesimal volume. And the electric flux density is related to electric field intensity, or I just usually call this the electric field, by this constant of proportionality called the permittivity. The permittivity depends on what kind of material you're working on or working with at the point in space in question. If you're working in free space, then we call that epsilon 0, and that's equal to 8.85 e to the negative 12 farads per meter. We will talk more about permittivity and why it matters and how it all works, but essentially you can think of both D and E as being proportional to one another. If you plug this relationship into Gauss's law here, you can then just express this in terms of the divergence of the electric field, which is equal to rho v divided by epsilon. All right, so what is Gauss's law actually saying? So you need to go back to your understanding of what divergence means. If you haven't seen my video on divergence explained, go ahead and check that out. But what this is saying is that the divergence of E, or the flux through each little cube, so you have a problem, you break it up into little cubes, the flux through each little cube, or the integral of E dot dA, is equal to the net charge inside that little cube divided by the permittivity of the little cube. What this is saying is that if there are no net charges inside the little cube, then the flux is 0. There's no flux if there is nothing inside the little cube. And that's even if there are net charges on the outside of the little cube. That might seem counterintuitive, but let me take you through a little thought experiment to make that more compelling. Okay, so suppose we have this little cube here. I drew it as very large, but imagine it's a infinitesimally small cube. And it has a charge inside it, centered at the origin here. You can see now that the divergence of this little cube, or the flux going out of it, it's going to have a net positive divergence or net flux flowing out, because you can see the flux is piercing out everywhere. So clearly you're going to have there's going to be a net outward flux in this case. But I want you to think about what happens if you shift the charge just a little bit. You still keep it inside the cube, but shift it a little bit. What will happen to the divergence or the flux? Well, what will happen is, my prediction is that it actually will be the same. It will be the same flux, no matter if you kind of move it around. As long as the charge is inside the cube, the flux will not change. And that's because if I bring it closer to here, then the integral of E dot dA on this side will be higher because the charge is closer to that wall of the cube. But on this side, it will be less because the charge is farther away from the cube. So the overall effect is that the total net flux coming out of that cube will be the same as if it was in the center. So what I'm trying to say here is that no matter where you position that charge, as long as there's some kind of charge inside this little cube, then the flux will be constant. But now, watch what happens, or think about what happens if you take that charge and you move it outside the cube. So now, the volumetric charge density inside this little cube is 0. There's nothing inside this little tiny cube, but there's a charge on the outside. And initially you might be thinking, okay, well, surely there's going to be still some flux, some outward or inward going flux into the cube if you integrate across all the sides. And I would beg to differ. If you think about this intuitively, I think it will make some sense here. So think about this. If the charge is on the outside, then what happens here is that here you'll do the integral of E dot dA over this side, and the field will be strong here because it's close to the charge. But then it will pierce through and it will spread out. And while the intensity will be less across these other sides of the cube, they will be all flowing out of the cube. Whereas in this case, on this side, the field is flowing in, but then it's flowing out. In, out. So when you integrate over the whole cube, it will end up actually being 0. So that's what Gauss's law is saying, is that if the charge is outside of that cube, then the net flux in that cube, the integral of E dot dA over the whole surface area of the cube, will be 0. You'll find that what goes in comes out. So it's going to be 0, and it doesn't matter what collection of charges you have on the outside. If there's nothing inside, then it will be 0. So that's how you can understand Gauss's law mathematically. You still might be wondering, though, how do you really get information about the fields coming from, like, a point charge, for example, on the basis of Gauss's law? So we will explore that in the next video. So thanks for watching, and I'll see you next time.